Chapter 10, the t-test for two independent samples, Part 5. In the previous video, we discussed the factors that influence our t-statistic, which have an effect on the conclusions we draw, whether we reject or fail to reject the null hypothesis. So I'm going to begin this lecture with a quick learning check to make sure that we understand the relationship between the components of the t equation when we are drawing our conclusions. Our ideal scenario is to have a large t value that falls in the critical region, which enables us to reject the null hypothesis. And for some time now, we've talked about what will influence the t statistic so that we can reject the null hypothesis. One of the things that we've discussed and should make sense and is very logical is the mean difference. The null says there's no difference between these populations that we are testing. So obviously, if we hope for a large t-value, we expect there to be a large mean difference. So therefore, considering these options, again, what we're trying to determine is which combination of factors is most likely to produce a significant value for an independent measure's t-statistic. So again, large mean difference is preferred because, again, we are testing for treatment effect or differences between populations that we're testing. So anything that says small mean difference would be incorrect. The other, and again, that's the mean difference is represented in the numerator of our t equation. The denominator is the standard error. Again, for each t-test, the equation is slightly different, but the concepts are the same. So the denominator represents standard error, which is reflective of variability. And for some time now, we've been discussing that low variability is ideal. And in terms of the equation, when we divide by a lesser number, the quotient, in this case, the t-statistic, will increase. So we want low variability, small variability. So given the other two options, this one says large sample variance and, large sample variance, and this says small sample variances, and we would conclude that this is ideal because that is not. When we have low variability, and variance is a function of variability. Variance and standard deviation reflect the variability within that distribution. And we know as researchers that the way that we can influence that variable is to use large sample sizes. So we have seen that larger samples would produce less variability. Less variability will lend itself to smaller standard error values and then produce higher t statistics. And again, higher t statistics mean that we are more likely to fall in the tails of the distribution, enabling us to reject the null hypothesis. So again, to summarize, the researcher hopes for large mean difference and low variability. And as researchers, we can have some influence on variability by increasing the sample sizes that we use to test our hypothesis. Next, we'll decide if the following statements are true or false. So first, if both samples have a sample size of 10, the independent measures t-test will have a degree of freedom equal to 19. Our equation for chapter 10 for degrees of freedom is as follows. We have n1 minus 1 plus n2 minus 1. So if we're saying that each sample is equal to 10, that would be 10 minus 1, 9 plus 9, and that gives us 18. So this would be a false statement. It would not equal 19. The degrees of freedom would actually equal 18. Next, true or false, for an independent measures t statistic, the estimated standard error measures how much difference is reasonable to expect between the sample means if there is no treatment effect. And this is a true interpretation of what the estimated standard error of the mean represents. Again, it's giving us a sense when we're looking at the distribution. The null would be centered here in the center where it says no mean difference. And the estimated standard error of the mean difference is kind of giving us a range of values that are still equivalent to 0 if the null is true, but just slightly different because of the fact that samples aren't always perfect. They're not going to be exactly what we would expect the population to look like. So it's kind of this wiggle room, or I often express as a standard or average difference between the center value that's representative of the null and what we would expect given sampling error above that center value and below. So again, this is an accurate interpretation of what the estimated standard error of the mean represents. So this is a true statement. I often define the estimated standard error of the mean difference in the following manner. I say that it's the average difference between the sample mean difference, which is M1 minus M2, and the population, the hypothesized population mean difference, mu1 minus mu2. And in this case, that's reflective of the null hypothesis, which is equal to 0. So it's the average difference between the sample mean difference and the population mean difference. Next, there are 3 assumptions that should be satisfied before you use the independent measures T formula for hypothesis testing. The first is the observations within each sample must be independent. 2, the 2 populations from which the samples are selected must be normal. 3, to justify using the pooled variance, the 2 populations from which the samples are selected must have equal variances. So the first 2 assumptions should be familiar from the single sample t-test presented in Chapter 9. As before, the normality assumption, or again relating to the normal curve assumption, is less important of the 2, especially with large samples. When there is reason to suspect that the populations are far from normal, you should compensate by ensuring that the samples are relatively large. So again, we've learned that as we increase sample size, the distribution of sample means becomes more normal. So we cannot use the t-test hypothesis test process if we are not working with normal distributions. So back in Chapter 8, we learned that as long as n is greater than 30, it will produce a distribution of sample means that is normal. Or if the original population from which we drew our samples was normal, then we don't have any reason to worry. The distribution of sample means, regardless of the size of n, will also be normal. The third assumption is referred to as homogeneity of variance and states that 2 populations being compared must have the same variance. You may recall a similar assumption for the z-score hypothesis test in Chapter 8. For that test, we assumed that the effect of the treatment was to add a constant to or subtract a constant from each individual score. So we discussed in Chapter 8 that we assume that the variability of before and after treatment are similar. And again, it's difficult to draw these identically in the same shape. They cannot be identical all the time, but instead of saying that before treatment variability looked like that and after it looks like this, again, these 2 demonstrate 2 different variability scores of a distribution. So again, in Chapter 8, we were just simply saying that the distribution is shifting either upward or downward because every score is, we're adding a constant to every score. So another way to think of it is, let's say we have an average score of 110 IQ scores. And then we administer some kind of mental exercise that increases IQ, and now we have scores of 115 as the average. And so here we would just simply understand that every person's score increased by 5 points, which shifted the distribution over, but had no impact or influence on the variability. The variability before and after remained constant. As a result, the population standard deviation after treatment was the same as it had been before treatment. We are now making essentially the same assumption, but phrasing it in terms of variances. So again, the concept of homogeneity of variance refers to this idea that the 2 populations that we're comparing initially have the same variances. So to better understand this, we should recall that the pooled variance in the t-statistic formula is obtained by averaging together the two sample variances. So it makes sense to average these two values only if they are estimating the same population variance. In other words, if the homogeneity of variance assumption is satisfied. If the two sample variances are estimating different population variances, then the average is meaningless. And here's a good analogy from the text. If two people are asked to estimate the same thing, for example, what you weigh, it is reasonable to average the two estimates. However, it is not meaningful to average estimates of two different things. If one person estimates your weight and another estimates the number of grapes in a pound, it is meaningless to average the two numbers. So again, because we're computing pooled variance, we have to adhere to this assumption that the initial population variances are equal. So you may wonder, how do you know if the assumption of homogeneity of variance has been satisfied? Well, one simple test involves just looking at the two sample variances. Logically, if the two population variances are equal, then the two sample variances should be very similar. And again, notice I said very similar, not equal. Again, because we're taking samples, samples aren't always going to be perfectly aligned with the populations. We expect some variation or natural discrepancies to occur when we cite sample statistics in comparison to population parameters. So again, the assumption is that the population variances are equal, and as a result, we would expect that the sample variances to be very similar to one another, but not necessarily equal. And we don't assume them to be equal because of the fact that we understand that when we select samples, there are natural discrepancies that occur when computing those sample statistics and relating them back to the population parameters. For example, if I can give you something to wrap your head around, if I were to think of the whole Southwestern College population, calculate their average age, I take a sample of a random sample of 10 individuals, calculate their average age. Most likely that average age of that random sample of 10 students will not be identical to the population parameter, the average age of all students. And it doesn't mean that that sample is not a representation of the population, just means that samples are not always going to be perfectly aligned to the population. So again, I will restate that the homogeneity of variance assumption states that we assume the variance of the populations are equal, and as a result, the sample variance should be very similar. So when the two sample variants are reasonably close, you can conclude what did I just do? That the homogeneity assumption has been satisfied, and that you can proceed with the hypothesis test for two independent sample means. For example, if we had a sample variance, and let's say it was equal to 1, and our second sample variance was equal to 1.25. Again, they're not equal, but they're close enough for us to then feel confident that this assumption has been satisfied. However, if we had two samples, and again, let's say the first one had a sample variance equal to 1, and the second sample variance was equal to 5, then we would have reason to believe that perhaps this assumption has not been satisfied. And we would conduct a test of variance to affirm whether or not this assumption has been satisfied. One objective procedure we can use to test whether or not this assumption has been satisfied is referred to as the Hartley F. Max test. This test is one of the simplest to compute and to understand. An additional advantage is that this test can also be used to check homogeneity of variance with more than 2 independent samples. Later in Chapter 12, Analysis of Variance, we examine statistical methods for comparing several different samples. So going beyond a t-test for 2 independent samples in Chapter 12, we'll consider multiple samples, more than 2. And this particular test is useful again to determine if this assumption is satisfied. So the following example demonstrates how we engage in an F-max test for 2 independent samples. So the F-max test is based on the principle that the sample variance provides an unbiased estimate of the population variance. The null hypothesis for this test states that the population variances are equal. So again, the null in this case says that the population variance for population 1 is equal to the population variance for our second distribution. Therefore, the sample variances should be very similar to one another. The procedure for using the F-max test is as follows. First, we're going to compute the sample variance for the separate samples. So we know that to compute sample variance, we need SS, again for our first distribution, SS1 over degrees of freedom 1. For our second distribution, variance is equal to SS2 over degrees of freedom 2. So that would be the first step, to calculate the separate independent sample variances. Next, we're going to use this new equation, the F-max equation, and we're going to identify the largest of the 2. So once we calculate the variance for both samples, then we select the largest and place that as the numerator and the smallest as the denominator of our F-max equation. Now let's for a moment consider what would this equation look like if this is true. And this is what we hope. In this case, we hope that the null hypothesis is true. And that's different from what we hope when we're conducting a t-test. Hypothesis the test is to provide support for the research hypothesis. In this case, we're hoping that the null is accurate, that the variability, the variance of the populations are equal. So if we use sample statistics, what would the F-max value look like if this null hypothesis is true? Well, let's just say that our variance for the first sample is equal to 5 and the second is equal to 5. Therefore, F statistic would equal 1.00, meaning that they're equal to one another. So again, and that's what we're hoping for. We're hoping that we don't see great differences. So a relatively large value for F-max indicates a large difference between the sample variances. So for example, let's say instead of showing that relationship, let's say this is equal to 10, and therefore our F statistic is equal to 2. In this case, the data suggests that the population variances are different and that the homogeneity assumption has not been satisfied. So we are going to take a look at the F distribution, which looks different than our normal distributions that we have been accustomed to using. And it is skewed in the positive direction, and in the center is a value of 1.00. And that illustrates that we have met the assumption that when we take this fraction, we will produce an F value equal to 1 and confirm this null hypothesis that these two population variances are equal. Now, if it's something very different from 1, then it's indicating that the population variances are not equal. And then what we'll do is put that F value to a test by identifying what a critical F value would equal given the parameters of this particular set of samples. To locate the critical value in the table, we're going to use table B.3 in Appendix B, which is the F-max table. So again, to locate the critical value, we're going to need this new variable referred to as k, and k represents number of separate samples. And for a t-test of independent measures, k will always equal 2 because we have 2 independent samples. When we get to chapter 12, that k value will change because we'll be comparing sample means for multiple samples, usually more than 2, which is why it's different from the t-test process. Next, we'll need degrees of freedom for each sample variance, and we calculate that by taking n-1. And this Fmax test assumes that all samples are the same size, and so you'll see the relevance of that in just a second. And then finally, we need the alpha level. The table provides critical values for 0.05 alpha and 0.01, and normally the test for homogeneity would use a larger alpha. So now I'm going to walk you through example 10.6 with the data that's provided to determine if we are working with 2 samples with similar variances that are representative of population with equal variances. So this is information coming from example 10.6 in the text. So we're going to take into consideration that we have 2 samples, each have a sample size of 10. And we're going to apply alpha at 5%. The degrees of freedom is equal to 9 because, again, as I mentioned, the Fmax test assumes that the samples are the same size. So we only use the degrees of freedom equation that states n is n-1. So in this case, we say that they're equal in size. 10 minus 1 is equal to 9. So that's one of the values that we need to enter the F table to find our critical F value. And the other value that we needed is K, and I indicated just a moment ago that K is the number of separate samples. In this case, we have 2. So we're going to use all of these pieces of information, which include the alpha level, the degrees of freedom, and K to find our critical F value from our F table in the appendix. So we'll do that next. So this is table B.3 in Appendix B, and please note that it says that the alpha at 0.05 is in light face type, and alpha for 0.01 is in the bold face type. So let's look at the markers here. So this column represents what K is equal to, and then we would enter it in this way using degrees of freedom. So we just indicated degrees of freedom is equal to 9. We're going to use alpha at 5%, which means of these 2 values, we're going to select the light face type, and K is equal to 2. So we're going to see where these intersect, and we find that, again, of these 2, the light face text is equal to 4.03, and that's our critical F value. So we set our critical F at the value we just found in our table, which was 4.03. And unlike the hypothesis test, we do not want our F statistic to fall in the critical region, this area in other words. We're hoping that it's close to the center, 1, because again, remember that the equation says that we're taking the largest variance divided by the smallest variance. And if they're equal, then the value should equal 1. And if they're pretty similar, it should still also be very close to 1. And notice that it's positively skewed because if we always have a larger number over the smaller number, it will never produce anything less than 1. It will always be 1 or something greater than, which explains why this distribution is positively skewed instead of having a normal bell curve shape that's symmetrical. So now that we have set our parameters for this particular test, let's replace variables in our equation. So we said that the Fmax is equal to the variability of the largest. So they gave us this information. So they told us the one sample variance is equal to 12.35, which is considered the larger of the 2. And then the other sample variance was equal to 9.15, which is the smaller of the 2. So again, whenever you have a numerator greater than the denominator, it always produces something 1 or greater. Okay, so now, again, we're hoping that we affirm the null. Again, the null said that the population variances are equal to one another, and we're using sample data to test that assumption. So in our calculators, let's take 12.35 and divide it by 9.15. And what we should get is equal to 1.349, or if we round, 1.35. So we see where that resides in our distribution, and we find that it's in this area. And that actually, and may be surprising given the structure of our hypothesis test that we've become accustomed to, this actually makes us happy, because we're saying that the sample variances are similar enough for us to conclude that the homogeneity of variance of the population, that assumption has been satisfied, that even though they're not identical, 12.35 and 9.15 are not identical, we have just put that difference, or the ratio of those two values, to the test to affirm that it's close enough to 1 that we feel confident that the assumption of homogeneity of variance of the populations has been satisfied, and that this is true, that they're equal to one another. And they're equal because of the fact that we just confirmed that the sample variances are similar enough and produce a ratio close to 1.00. Had it been calculated that it was equal to 5, let's say, for example, let's say it was equal to 5, f equal to 5, then in that case, we would not be able to affirm the null, which says that the population variances are equal. And therefore, we would not be able to proceed with a t-test for independent sample means. So interestingly, we would, in this particular test, fail to reject the null. And you can think of it as we accept this idea that the variance of the two populations is equal, because the null said they were equal. We did not fall into the critical region. We did not want to fall in the critical region for this type of test. Therefore, we failed to reject the null. And you can interpret that in your head as we accept the null. We accept that the variances of these two populations is equal. And as I just mentioned, would enable us to proceed with a t-test for 2 independent samples. So I'll end this lecture with a brief learning check. Let's consider this statement. For an independent measures research study, the value of Cohen's d, or R squared, helps to describe, and we'll fill in the blank. Again, Cohen's d and R squared are measures of effect. So A and B are kind of similar. They say the risk of type 1 error or the risk of type 2. And in the past, when I presented Cohen's d and R squared, I indicated that those measures of effect can help illuminate if we have, in fact, engaged in one of these two types of errors. But it does not describe the risk of a type 1 or type 2 error. So these two would not be accurate. Let's consider the next one. It helps describe how much difference there is between the two treatments. Well, perhaps. Let's read the next one. Whether the difference between the two treatments is likely to have occurred by chance. Well, that's not for us to be able to determine, so this would be incorrect, and this one is the logical answer. The measures of effect tell us or describe how much difference there is between the two treatments. Again, the Cohen's d is always read. We're expressing the mean difference in standard deviation units. We're indicating the shift that we see, for example, before treatment, after treatment, or between two different treatments. And R squared represents the percentage of variability accounted for by the treatment or accounted for by the difference in the quasi-independent variable conditions. So again, this is the best answer of these options. The measures of effect help to describe how much difference there is between the two treatments. And then finally, let's consider these two statements and determine if they are true or false. First, the homogeneity assumption requires that two sample variances to be equal. Well, we just had a very extensive conversation about the homogeneity assumption, and the assumption is that the two population variances are equal. So not sample, population variances are equal, and consequently we would assume the sample variances are very similar. Okay, so again, the sample variances aren't going to be identical to the populations. We understand that, accept that because of the natural discrepancies in selecting scores for a sample compared to having all of the scores in a population. So this is a false statement, and the reason again it's false is because the homogeneity assumption requires that the two population variances will be equal. Next, if a research reports that T with degrees of freedom equal to 16 is equal to 1.98, the probability statement is greater than alpha, then the null was rejected. And I have indicated before that when the probability statement shows P is less than 0.05, or I should just be generic and say alpha, whatever alpha is equal to. When it's less than alpha, then we reject. When P is expressed as greater than our set alpha, we fail to reject. So what do we have here? We have greater than alpha. Therefore, our conclusion would not be to reject. It would actually be to fail to reject the null. So this too is a false statement. So again, in your notes, you should make sure you have this written down. Students often get confused about how to express that probability statement. Again, if we're rejecting the null, we're talking about values that are very rare and occur in the tails. They have very low probability, so less than whatever we set alpha at. If it's falling in the center region, right, then it's greater than what we set alpha at, and we would indicate that the probability is greater than alpha. So make sure that you understand the difference in what this probability statement indicates in terms of what we're doing with the null hypothesis. And that concludes Chapter 10. Now, this particular lecture is not as relevant to the homework problems that we have for this chapter as they will be relevant towards what we learn in Chapter 12. So this information is presented in this chapter, Chapter 10, in anticipation of what we're going to learn in Chapter 12. So you won't see a lot of examples of calculating F-max ratio, but again, it's good to introduce new material early and give you a little preview, because these concepts will come up in Chapter 12, which is analysis of variance, and enables us to compare multiple samples beyond simply just comparing two samples. And again, this concludes Chapter 10, Lecture 5.